Hello everybody. So what we're going to be doing today is we're going to be looking at improper integrals. So you might notice that you have two homework assignments, a homework 18 and a homework 19. And so I'm calling this lecture 18 and 19 just because I don't want to do two videos. And also I don't want the numbering for the lectures to get off of the numbering of the homework. So I want them to match. So lecture 18 and 19 to go with homework 18 and 19, which are on the same topic, improper integrals. Okay, so let us go ahead and talk about improper integrals. So yeah, hold on a second. There we go. Okay, before we start, something that I want to mention is just some stuff about limits. So this is not about improper integrals, this is about limits, which we'll need. Limits. Okay, so the basic idea that you're going to need to know is that if you take the limit as, let's say, x goes to infinity of something like this, x, of course that limit's going to be infinity, right? And there are a lot of functions like that, like the limit as x goes to infinity of x squared. Of course that's going to be infinity. The limit as x goes to infinity of e to the x, that's going to be infinity, and so on, right? So that's not a problem. But there's some other limits as x goes to infinity that we just want to be on the same page for. So like if I do the limit as x goes to infinity of 1 over x squared, for example, what would that be? Well, you would have 1 over infinity, right? Now technically this is wrong to write because infinity is not a number. You can't put infinity in the denominator of something. So this is actually not quite a proper way to write this. Not, real math. You can't just have 1 divided by infinity. That doesn't make sense. But you can still think about 1 over infinity, and if you do, you should know that that is 0. Okay, so that's the basic idea you need, is that if you have 1 over infinity, you're going to get 0. Now, besides those, there's a couple of, I'll say, not weird functions, but a couple of functions that are not like polynomials that you may need to understand how they work. So let's see here if I can get a picture up. I don't know if I can. I am not smart. That's not true. I'm a freaking genius. But what I don't know is I don't know how to use the computer that's sitting in front of me. All right. Oh, is that going to work? What? It did work. I've got a picture. Now, how do I do something with it? I want to move the picture. Let me move the picture. All right. Yeah. All right. So that's fine. That's good enough. Let me make keyboard go away. Okay. You can't see what I see, so that didn't make any sense to you. I hate the way that's just kind of floating there. I'm gonna draw an outline so it doesn't look like it's floating. Okay, there's a graph. That was dumb. So what we have here is the graph of a function. Now this is the graph of y equals tangent inverse of x. Okay, and what you can notice about it is that out this way and out this way, it just levels out, right? And you can even say what the level is. So this point right here, this is up at pi over 2. It's not written here, but you can see where pi is, right? Pi is right here. So that's pi over 2. And the one down here, this is negative pi over 2. And so if you're looking at this graph, trying to decide what it means, you can probably agree that if you do the limit as, let's say, x goes to positive infinity of tangent inverse x, from the graph, you can see it leveling out at pi over 2. So that limit is pi over 2. And also, you can see that the limit as x goes to negative infinity of tangent inverse x, well, that's the one down here. So that's down at negative pi over 2. Okay, and so you just get that from the graph. All right, so that's one graph you need to know. Now, there's another one. Let's see if I can get this one up. Do that. How do I do this? I just do that? No, that doesn't work. That doesn't work. Stop it. Okay, that's fine. Where is it? I think this one. Okay, so here's another graph. Let me see if I can move it again. Stop it. Select it. Move it. I don't need it that big. Keyboard, go away. Do that so it's not as distracting to me personally. And let's look at this. So again, on this graph, this middle value here you can see is pi over 2. Now, what is this function? Well, I'll tell you. This function right here, this is the graph of secant inverse x. That's what the graph is. Okay? So from this graph, you should be able to see that the limit as x goes to positive infinity of secant inverse x is pi over 2. And also, the limit as x goes to negative infinity of secant inverse x is what? Pi over 2 again, right? Because it's out here. They both go to pi over 2. They level out at the same place. So you're going to need to know those limits in order to do the homework. And you don't want to have to think about them. You just want to be able just to reference a picture. Now, if you forget these or something, then I would just recommend that you go to Desmos and actually just plot them. Or if for some reason you have another function that you need to plot, you can just go to Desmos and plot it. Okay, so yeah, so that's that. Now, having said that, now we can actually start talking about our topic, which is improper integrals. So I'm going to write this. The lag is immense, so I'm about to close this and open it up again. And I'll probably have to rewrite those words that I just wrote. I'm going to hit back, and then I'm going to try it. Think that made a difference? I don't know. Yeah, it did. Saved it. I'll remember to do that from now on. Okay, so what are improper integrals? So improper integrals are definite integrals. So they have limits of integration. That have infinity involved in some way. Okay, now how is the infinity going to be involved? Well, basically there are only two types, and the two types are why there are two homework assignments, really. So there's like a homework 18 type and there's a homework 19 type. They don't really have names, by the way. Some books will try to call them type 1 and type 2, but there's no reason why one would be type 1 and one would be type 2, so don't worry about that. But there are two types, and they are as follows. So the first type is going to be one where infinity is in the limit of integration. So I'm going to say infinite limit of integration. So I'll write an example and you'll say, oh, okay. There you go. That's improper because there's an infinity as a limit of integration. And it could have been the lower limit, it doesn't matter, but just as a limit of integration. Now, the other type is going to be an integrand. Integrand is the thing you integrate. So an integrand that becomes infinity or becomes infinite. And that's going to be, usually it's just a divide by zero. So usually a divide by zero. So what that might look like is, like, if I say integral from 1 to 5 of 1 over x minus 5. Okay? Because if you plug in a 5, you're going to get a divide by 0, right? So that's an issue. So there's a 5, and then when you put it in there, you're going to get divide by 0. So those are the two types, and we're going to look at them. So let's look at the first type. Okay, that's going to be the homework 18 type. First type. Okay, so the idea is this. So there's a way to handle it. So consider integral a to infinity of f of x dx. So the way you deal with the infinity is with a limit. You deal with the infinity formally by rewriting it as a limit. Okay, so what you'll have to do is you'll say, well, you take away the infinity and you replace it with a variable. Okay, so I replaced it, I took away the infinity and I put a b there. And then what you do is on the outside, you just say limit as b goes to infinity. And then you do the integral as normal. And honestly, that's it. Like, that's it. Okay, so let's just look at a very basic example of how to do this. So if I had the limit from 1 to infinity of, I'm going to say, what am I going to say? Let's just say e to the negative x dx, right? Then what you would do is you would rewrite. So you'd have a limit as b goes to infinity of integral 1 to b of e to the negative x dx. Now, by the way, I used a b there for the top limit, and the reason I do that is just if I'm replacing a top limit, I'll usually do it with a b for the variable, and if I'm doing a bottom limit, I'll usually use an a for the variable, and that's just, you know, easiest for my brain to keep track of, right? B's are top limits, A's are bottom limits. So that's just how I tend to do it, but it doesn't, it doesn't matter what letter you use technically. So from there, you're just going to do the integral as normal, ignoring the limit until the end. So on this one, you would just say, well, what's the antiderivative of e to the negative x? Well, it's e to the negative x over negative 1, but that's just negative e to the negative x. And then you go 1 to b. Again, we're just rewriting this limit. You plug in your limits of integration. So you put in the b, you get, put in the b, you get negative e to the negative b minus negative e to the negative 1. Okay? I guess I'll move over here. So what that is, I'm not going to take the limit quite yet. What that is negative e to the negative b is negative 1 over e to the b. Right? A negative exponent is a positive exponent in the denominator. And then you have minus a minus, so that's a plus, 1 over e. Right? At this point, once you've worked out the integral, now you're just going to evaluate the limit, just as your last step. Okay, so that's where you need to know some basics about limits as things go to infinity. So what you should do is you should just say, well, this term right here, when b goes to infinity, that's 1 over infinity. I'm going to write that. Again, you're not technically allowed to write that, but I am. The whole point is that this is 0. 1 over infinity is 0. So your limit is 1 over e. So that's the integral. Now, a little bit of formal notation about this. So notation or theory. When you evaluate an improper integral with a limit, using a limit, I'll say, if you get a number at the end like we just did, we say the integral converges to that number, whatever that number is. Those are quotes. Okay? If the limit fails to exist, so for example, so you get, plus infinity or minus infinity, or just doesn't exist for some other reason, we say the integral diverges. All right, so diverges if you don't get a number, and if you do get a number, then the integral converges to that number. So those are your two choices. So every time you have an improper integral, either it's a convergent improper integral or it's a divergent improper integral. And so all over in the homework, you'll see integral converges to 0, integral converges to pi over 2, or integral diverges. So it either converges to a number or diverges. Those are your two choices. Okay? So we need to understand that. All right, let's see what else can I say about this. A few things, right? Many things. So couple of things. So we did, I was going to say we did 1 over x squared, but we didn't do 1 over x squared. Let's do a couple quick examples here. So I'm going to do 1 to infinity of 1 over x squared dx. Well, let's just do that one. We're going to do 1 over x squared, 1 over x, and 1 over square root x. So we're going to do 3 of these real quick. So what do? Right? You see the infinity, that's wrong. You've got to fix it. So limit as b goes to infinity, 1 to b. I'm going to rewrite that 2 as x to the negative 2 because I know that's the easiest way to integrate it. So then you have a limit as b goes to infinity of, we need the antiderivative. The antiderivative of x to the negative 2 is negative x to the negative 1, right? Add 1 to the power, divide by the power, from 1 to b. I'll come over here. So that's the limit as b goes to infinity of putting your numbers. So you have negative b to the negative 1 minus 1 to the negative 1. So you have the limit as b goes to infinity of, negative 1 over b plus 1. So what's that limit going to be? When b goes to infinity, that's hard to read. When b goes to infinity, you're going to have 1 over infinity. 1 over infinity is 0. We already talked about that. So 1 plus 0, so you get 1, right? So integral converges to 1. All right. Now you can say that the integral is equal to 1. That's okay. You don't have to say converges to 1, but you can. Okay, let's do this. Now what I'm going to do is I'm going to just change the exponent there to a 1 instead of a 2. Right? Now we have to do it the same way. And then I'm going to draw some pictures for you, and hopefully they will help make sense of this. So you rewrite it as a limit, which we just did, but now the antiderivative of 1 over x is actually a natural log. Absolute value 1 to b. So you put in your b, you put in your 1. I don't have to use an absolute value anymore because b is positive. So we have that. And then now we need to know what the limit is. Now, the natural log of infinity we didn't talk about up at the top, but the natural log of infinity is infinity. So this is going to be infinity minus, and this happens to be 0, so infinity. What does that mean? It means that the integral diverges. Okay, so that one diverges. And one more, and then we'll start talking about stuff. All right, so let's do this one. So again, you can write it as a limit. In fact, you are required to write it as a limit. That's the rules. 1 over square root x is actually x to the negative 1/2. You're going to use the power rule here. So you add 1 to the power, you get x to the positive 1/2. Divide by positive 1/2. So the antiderivative is actually 2 square root x. I'm not going to do it in more detail because we have a lot of these to do. Then what are we going to do? We're going to plug in our limits of integration. 2 square root b minus 2 square root 1. If b goes to infinity, you're going to have 2 times infinity from this. So that's just going to be infinity minus 2. But that is still infinity. So this also diverges. All right. Now what I want to do is talk about these a little bit. Like what happened, what happened with these? Why did they come up the way that they came up? Well, if you look at a graph, I have a graph, but I think it's actually going to look better if I draw it because I didn't like the way that those other graphs that we just did look. If you look at the graphs of these functions, 1 over x, like we're only on the positive half here. 1 over x does something like this. Okay? I'll say that that's 1 over x. And if you look at the graph of 1 over x squared, then they go through, there's one point that they go through that's the same, 1, 1. So I'm going to say that this is 1, 1. So 1 over x squared goes through that point as well, right? And the curve, though, looks a little different. It looks like that. That's 1 over x squared. If you look at the curve for 1 over the square root of x, looks basically the same. Somebody just emailed me, one of you guys. Not happy about that. No, just kidding. Not really. No, just kidding. Looks like that. So the thing is that when you do one of these integrals from 1 to infinity, what you're actually doing, remember, an integral is an area under the curve. So when I'm doing the integral from 1 to infinity of 1 over x squared dx, I'm actually calculating this area. And that area, actually, think about it, it goes on forever, right? That's what we're doing. It goes on forever. How are you calculating an area that goes on forever out to the right and getting a finite number? That's a weird thing, right? Somehow you do that and you get 1. We just did it, so we know. But that's weird. That's weird that that happens, okay? Now, if you look at, let's say, the 1 over x, it's the same idea, right? Like if I do the integral of 1 over x, I'm also going to be calculating an area. But if you look at the area that you're calculating, it's more area, right? It's more area there. And so this one, from 1 to infinity of 1 over x dx, we know it was bigger than 1 because I can see that it's more area, and actually it's infinity. Okay, so the graphs look the same-ish, like they both go to 0, out to the right, that kind of thing, but somehow this one comes up to be 1, and then this one comes up to be infinity. And it turns out that this is kind of a cutoff value. So there's an integral that you can call p integrals. I don't know if they do in your book, but p integrals. So a p integral is an integral from 1 to infinity of 1 over x to the p. And they use a p, so that's why they call it a p integral. And so basically, if on any of these, if p is greater than 1, if p is greater than 1, then it's just like this one that actually converged. So if p is greater than 1, the integral converges. And if p is less than or equal to 1, the integral diverges. Okay, and so every one of these integrals is either like the first one, the second one, or the third one, right? So the reason it worked out the way it did was because, take a look at this right here. You have a negative exponent. You do the antiderivative, and you still have a negative exponent, right? After the antiderivative, this was still negative. The exponent was still negative, right? And because it was still negative, that meant when you plug in your infinity, it was like this, you were putting infinity in the denominator, right? So because the exponent was negative, you were plugging infinity into the denominator. And if you look at the square root x version, you start out with a negative exponent, but after the integral, it's actually a positive exponent, positive 1/2. And because it's a positive exponent, that means it's in the numerator, not the denominator. So when you plugged in your infinity here, it wasn't 1 over infinity, it was infinity. And that's why this one came up infinity, right? So in the first case, the infinity ended up in the denominator. And in the third case, it ended up in the numerator, basically. And so the cutoff point where it switches between numerator and denominator is just 1. So greater than 1 means that after you add 1 to the exponent for the power rule, it'll still be negative. Less than 1 means after you add 1 for the power rule, it will be positive. If that sounded a little bit backwards to you, it's because the p is in the denominator. So p greater than 2 means actually less than, like a p of 2 would mean actually the exponent is negative 2. So if it sounded backwards, that's why. Okay, and it's easy enough to prove this, but we did examples of it, and I think that's going to be good enough because we have a lot more to cover still. So, yeah, so that's good to know. It will help you solve problems if you know that to start with. Okay. I'm looking at a couple of problems here. All right, I see a few of these. We should talk about these. You are going to see some, you will see some problems where both limits are infinite. Where will that happen? Well, or what will that look like? It'll look something like this, like negative infinity to positive infinity of whatever they want. So, maybe it's, e to the negative x, whatever it is. It doesn't matter. The point is infinity, infinity. All right. And so basically the right way to do it, there's the right way to do it, and then the way that I sometimes do it. The right way and other ways. So the right way to deal with this is as follows. The correct way to deal with this is, so I'm not going to use a specific example here because this is just notation. But what you do, if they're both infinite like this, is you use a property of integrals that says, like, you've seen this property before, right? Like integral from a to b plus the integral from b to c equals the integral from a to c. You have seen that, I guarantee it. What you do is you basically, I don't want that there though, sorry, you gotta go. What you do is you split the integral. So it goes from negative infinity to infinity, but that's the same as just saying, well, what if we do one integral from negative infinity to 0, and then we do another integral from 0 to infinity, and then when we add them up, we'll get the total integral. So you split the integral up, and now you have two integrals, and then you can solve them both separately with the same idea that we've already used. So like you could use limit as a goes to negative infinity, negative, I want to write that so it's clear, negative infinity, a to 0, f of x dx, plus limit as b goes to infinity, 0 to b, f of x dx. And then you just work these out separately. I will make a little note here for you guys. Note. In order to converge, they both need to give you a finite number, right? Otherwise, like it doesn't, like if you do the first one and you get 3, and then you do the second one and you get infinity, well, 3 plus infinity is infinity, so there's still no limit. Okay, so in order to be convergent, or I should say just in order to converge, both integrals must converge. So, if the first one you check diverges, then just stop because it diverges. Okay, so if the first one you check diverges, you don't need to bother with the other one, because if one of them diverges, they both diverge. No, that's not right. If one of them diverges, the whole thing diverges. The original one diverges. So, but that's the formal way to deal with it. And so you should be aware of this. Now, for some reason, they like to give you problems, honestly, where I'm not even necessarily going to use a limit. Here's kind of a weird one. Well, yeah, let's do this. They give you this integral a bunch of times, and so because they're going to make you do it a bunch, right, you probably want me to do it. That makes sense to me. That's supposed to be, I wrote 7e to the 7, but that's supposed to be 7e to the x. All right. Now, if you look at this, this looks like a pretty complicated integral. It's not really. What it needs is it needs you to do a substitution. That's all it really needs, is a fancy substitution. So the correct way to do it, I keep saying that today, the correct way to do it. The reason I keep saying the correct way to do it is because you can really kind of do these problems without writing them in terms of limits. It's just that you're being bad when you do it. So that's why. So here's the thing. This right here, the 25e to the 2x, is this. If you take 5e to the x and you square it, you get 25, e to the x squared. But when you raise something to a power, you multiply the powers. So you need to recognize this right here as actually being 5e to the x quantity squared. Okay? You just have to recognize that. And again, you're going to have to do it a bunch of times, so it's not that bad. Just follow the pattern there. So that's what you're going to get. Then you can do a U-Substitution. What U-sub? You're going to use U equals the 5e to the x. And the du is going to be 5e to the x dx, right? Because the derivative of e to the x is just e to the x. But that means du over 5 equals e to the x dx. Now, it's a little bit confusing for people sometimes because there's an e to the x in u and there's an e to the x in the du. So make sure you understand. Oops. Every time. Your u is e to the 5x. You're going to substitute that right there. I don't have a dx here. Now I do. Your du over 5 is e to the x dx. So that's going to be this, right? So your du is going to end up in the denominator, and the u is going to end up down in the the du is going to be in the numerator, and the u is going to be in the denominator, and you kind of just have to know that that's the way it's going to work out for these. Otherwise, you might get it wrong. So I'm going to rewrite this. I'm going to leave the limits off for the moment. So I have 7 e to the x dx. E to the x dx is du over 5 over, in the denominator, 1 plus u squared. Okay, so that's fine. But we should figure out the limits of integration, right? Remember, when we do a U-Substitution, we should change the limits of integration. So I want to do that. So let's look at the limits of integration. So we're not even dealing with the fact that it's improper yet. We're just like trying to do a U-sub on this. So what you have is, what's your top limit? Your top limit is x equals infinity, right? Well, if x is infinity, you plug that into your substitution, u would be 5e to the infinity. Again, you're not supposed to write that, but I don't want to write a limit here. It's a waste of time. So x is infinity, u is 5e to the infinity. What's 5e to the infinity? Hopefully you can agree that it's infinity. So we got, why? So that's the top limit right there. Now the bottom limit was negative infinity. So if you plug that into u, you get u equals 5e to the negative infinity, which you need to recognize is 5 over e to the infinity. What's that? Well, we talked about that. Like 5 over infinity is going to be 0. Right? So you get those, 0 and infinity. So over here in your answer, right? Or not your answer, in your problem, change your limits to 0 and infinity. Okay, so change the limits to match your substitution, and then we can continue on. So this is actually now 7 over 5 integral from 0 to infinity of du over 1 plus u squared. Now is the time where we get to actually deal with the fact that it's improper. So rewrite it. So what are we going to get? We're going to get 7 over 5, or actually I shouldn't do that. I can, but limit as b goes to infinity of 7 over 5 integral 0 to b du over 1 plus u squared. Okay, now you should recognize this. You need to recognize this integral. Again, you should recognize this integral. This integral is going to give you an inverse tangent. Right? Okay, so you need to recognize that when you see it. And in fact, it's the simplest one. It's tan inverse just u. There's no a or anything, so it's just tan inverse u. And this needs to be evaluated from 0 to b. So limit as b goes to infinity, 7 over 5. Tan inverse b minus tan inverse 0. Right? We're not going back to x because that was the whole point of changing the limits of integration, was that we don't have to go back to x. Okay, so now what? Well, now you need to evaluate your limit. And that's why we talked about tangent inverse of infinity. Right? We put the graphs on here, up here, way up here. Right? When x goes to infinity, tangent inverse goes to pi over 2. That was so when you get down here, you can just do it. So b goes to infinity, so this is going to be 7/5. This one's going to be pi over 2 minus tangent inverse 0. Well, we didn't talk about that. Let's go look at the graph. Right there, right? Tangent inverse of 0 is actually 0. Goes through 0, 0. Back down. So that's 0. So you do all that work, you get 7 pi over 10. And that is that. Okay, now let me look real quick. Nope, they do it exactly the way I would do it. No, that's not true. They split it up. Yeah, so they did it slightly different than me. They actually followed my directions up here, where I said you can split it up. They split it up, and then they did each integral the way I did this one. I didn't split it up. I did the U-Substitution first. And because I did the U-Substitution first, I didn't have both of them infinite anymore. I only had one of them infinite. Of course, you get the same answer either way, so this was perfectly fine. So after I did the U-Sub, I saw I didn't need to split it up, so I didn't bother. All right. But anyway, that was just a problem. Nothing special about it. Okay, so you have some of those. Um, Now, here's one big thing that I can't really. There's. I wish this was not on the homework. I wish it was not on the homework, but I don't get to pick the problems. They picked the problems, and it's a topic that is from Math 4A, but not every Math 4A instructor goes over it. And so now we have to talk about it a little bit. So this is just kind of a separate topic, separate topic. I'm going to say that a couple times just to prove I can. All right, separate topic. What separate topic? So the separate topic is going to be the very, very basics of what we call solids of revolution. I'm telling you what it is so you can look it up if you want to. Specifically, we're going to be doing disk method. Okay, and I'm not really going to go over it in too much detail. I'm only going to go over just enough to do the homework problems. I think you have 2 of them. Okay, so what is it? I mean, unless you get it wrong, then you have a million of them. Here's the idea. They'll give you a curve, like they say, rotate. Let's say y equals, I'm just going to do 1 over x from, I'm going to say x equals 1 to x equals 2 around the x-axis. Okay. And this is like an example, except I'm not doing calculations yet. I'm just going to draw pictures. So this to give you an idea of what the solid of revolution is. So what a solid revolution is, you got your x and your y-axis. You've got a curve here, right? Y equals 1 over x. So the 1 over x curve, something like that. Okay. Now I say from x equals 1 to x equals 2. So I'm just going to call this 1, and I'm going to call this 2. Okay. So there's a region here. I need a different color. One that's like a little lighter. Okay, so you have a region there. Now, when I say we're going to rotate it around the x-axis, what I'm talking about is if you take this section of the curve from here to here, the section that we're talking about, and you rotate that entire line in 3D space around this axis, right? So this point goes all the way around, and this point goes all the way around, and then what you end up with is sort of like a weird shape like that, like a funnel, kind of. Okay, and so like this is actually a circle here, but we're looking at it like on the edge, and it's a 3D shape. And I can show you maybe better pictures if I go here. This is a computer website that has like rumors about new video cards and stuff. You guys don't care. I don't have a saved image of this, so I'm just gonna find one. Pictures. Wikipedia. Wikipedia sucks. Paul's notes. His pictures are basic usually, but they'll work, right? So let's look at this. So like you have a curve, you rotate it around the axis, and you get a picture like this. And so that's all we're talking about, is something like that. Okay, so you should be able to visualize this a little bit. That from the curve that we have up top, that it ends up with the shape that we have here, right? You're rotating it in 3D space. And the question is always the same. It's how do you find the volume of that? Okay, so does this make sense? Now, it turns out that the way to find the volume of this is as follows. If you take a little slice out of it, right, like a little rectangle there, and you take that piece, I'm going to draw it out here, and you take just that piece and you rotate just that around the axis, you get, not that, if you take just one rectangle, what you get is, like, why can't I know why I can't draw it, because it's where it is, there's something in the way and I can't reach it. But you end up with this kind of shape when you rotate it around the axis. So it looks like a coin, like basically like a coin on its edge. Does that make sense? Like this is the sides, and then this is like the face of the coin. That's what you get. And this is a disc. Well, a disc is technically not a 3D shape, but you could, like, you call it a disc. So you can call that a disc, which is why this is going to be called the disc method, except I spelled it like compact disc instead of actual disc. And the whole volume formula is based off of this. Now, in order to get the volume of this, it's technically a little cylinder. You would need to know the radius, and also you need to know this thickness, which I'm going to call delta x. Now, if you did know that, then the volume of this little disc is going to be the area of the face, which is pi r squared, right? The area of a circle, that's going to be the face. And then to get the volume, you just multiply by basically the height of that cylinder. Okay? Now, you don't need to know this, okay? This is just where the formula comes from. But that's not the whole volume. That's just this little piece. Like this is it. This is just that one little piece. If you rotate just that around, that doesn't look like that. But I was trying erase. Ooh. Okay, stop erasing. Stop erasing. Okay, so that's just one little disc, is one of these guys, not the whole thing. And so actually, if you take this and you say, well, we actually need to add up all of them from 1 to 2, then you do it with an integral. And basically what your integral is going to be an integral from a to b. In this case, it would be 1 to 2. I'll draw it 1 to 2. And then you integrate this, pi r squared, and the delta x becomes a dx when you do an integral. Now, I understand that that's not a proper derivation, but the idea is this is the formula that you're going to use. And what the r is the distance from the axis up to the curve, which sounds complicated, but the distance from the axis up to the curve is simply going to be the y value there. So like if I said that the curve was y equals 1 over x, then that would be the r. Okay, so in general, the disc method so you've got your curve wherever it is, you have your A, your B, you can rotate it around the axis, that looks terrible, but you know. So you rotate that around the axis, and you have an r here. Then the volume is the integral from a to b of pi r squared dx. And the r is generally just the equation of the curve. Okay, that's not a full-on explanation, but it's enough to do the problems that you're going to have to do. So let's do one, and then we'll know how to do it. Okay, so example. Find the exact value of the solid obtained by revolving the region bounded by f of y. They already even couldn't make it as easy as our example. E to the negative y over 4 square root, that was a square root, dummy, square root e to the negative y over 2 plus 1, and by y greater than or equal to ln 4 around the y-axis. All right, so first thing is everything's a y instead of an x. So I'm going to cheat. I'm going to put my y-axis here. And this is my f of y-axis. And there's no x's anywhere. Okay? So this curve just does this. Okay? That's all it does. So this is my f of y. Okay? And I don't have a variable to call it like x equals f of y or something, so I'm just labeling it f of y. Now, they say y greater than ln 4. So they're putting ln 4 somewhere on here, which is like this, and greater than that is this way. And this goes on forever out this way, okay? And then they want to take this and they want to revolve it around the y-axis. Now remember, I put the y-axis where the x-axis normally is, so around the y-axis is just this, okay? So you're going to get this kind of trumpet shape. Like that. That's the shape, okay? Now, you need to set up the volume of it. So what you're going to do is measure the radius. Now remember, I said that the radius is actually not going to be that hard. This, I should really use a color that you can see. That's not really good. There we go. Your R is just there, from the axis up to the curve, okay? And we know that the volume is an integral from a to b of pi r squared. Now normally it would be dx, but ours is dy because that's just the variable that we have. Okay? Then for us, we're going from here's our bottom limit, and then we're heading up forever in this direction towards infinity. So my limits are ln 4 and infinity. Okay? And then my integral is pi r squared, but r is actually just the height of the curve. So my r is actually just e to the negative y over 4 over square root e to the negative y over 2 plus 1 quantity squared, right? It's r squared dy. Now that looks like a really annoying integral, but that's what they're being asked. You're being asked to solve. Okay. Now you solve. I'll just pull the pi out. We need to square this. Now when you square e to the negative y over 2, you're going to get e to the negative, it's going to be 2y over 4, right? Because you multiply the 2 by the power. And then when you square the denominator, you're squaring the square root, so that goes away. So you have that. So you've got e to the negative y over 2 over e to the negative y over 2 plus 1 dy. And this looks a lot like the previous one we did. That was an arctangent, but this one's not an arctangent because you may notice that this and this are identical. So you actually want a different substitution. You want u is negative y over 2 plus 1. du is negative 1/2 e to the negative y over 2 dy. You move the 2 over, negative 2 du is e to the negative y over 2 dy. So my integral is pi integral ln 4. Actually, no, it isn't. We have to change the limits. So we actually have two different e to the y over 2's. Man. This one along with the dy, right? Those go together. So e to the y over 2 dy is negative 2 du on top. On the bottom, you just have u. And then your limits of integration, let's do them right here. The top limit used to be, what was it? The top limit was y equals infinity, I think. Yeah, it was infinity. That's the top. Which, if you plug that into u, you get u equals e to the negative infinity plus 1. What's e to the negative infinity? We've done that once or twice already today, so that's 0 plus 1. So that's actually just 1. So the top limit is 1. And then your bottom limit was y equals ln 4. So you put that into your substitution. U is e to the negative ln 4 over 2. That's a little bit harder to calculate, but you can do it this way. E to the negative 1/2 ln 4, e to the ln 4 to the negative 1/2 using log rules. Those cancel, so you get 4 to the negative 1/2. So that's 1 over 4 to the 1/2, which is 1 over the square root of 4, which is 1/2. So your bottom limit is 1/2. Wait, let me think. I don't know. Let's try it. I was going to make you do it, and I was going to just double check in my brain that this was right, but I don't know. Now notice this is not even improper anymore, by the way. So you take the negative 2 out, integral from negative, no. Is that actually right, by the way? Let's just check. I think that's right. Could have made a mistake somewhere. Take the negative 2 out, so we have 1/2 to 1 du over u. So you have negative 2 pi. The antiderivative of du over u is ln u from 1/2 to 1. So negative 2 pi ln 1 minus ln 1/2. There's a mistake here. There's a mistake here. Hold on, let me just check this. There's a mistake here. Where did I make the mistake, guys? Somebody tell me. All right, have to look. So that is right. Negative 2y over 4. So negative y over 2. That's fine. That's negative y over 2. That's fine. So this is still good, where So the only place I see a mistake could be is in the substitution or the limits. So u is negative y over 2 plus 1, sure, du. So e to the negative y over 2 times the derivative of what's inside, which is negative 1/2. Okay. So you move the negative 1/2 over as a negative 2. So I agree with the substitution. I agree with myself, I guess is what I'm saying. So negative 2 du over u, fine. So I feel like the only place that it could be is right here. So what did I do? Could I have done this limit wrong somehow? It was negative y, which was ln 4. That's right. Over 2. So that's negative 1/2 ln 4. So that's ln 4 to the negative 1/2. Take up this power. Let's cancel. 4 to the negative 1/2. 1 over 4 to the 1/2. Huh. I do not understand. Because what I'm going to get is this. I'm going to get negative 2 pi. This is 0. And then minus ln 1/2. ln 1/2 is just ln 1/2. So you have negative 2 pi, actually negative, so 2 pi ln 1/2. And this can't be right because ln 1/2 is negative. So there's a mistake here. Somehow this is supposed to be, well, if I take the 2 up, no, it still won't work. Yeah, so somehow what happened is the top here is supposed to be a 3, and somehow I don't have the 3. Somehow I lost a 3. And I don't know why. Okay, well I can't fix it because this is already taking a long time. So there's a mistake. The answer was supposed to be actually pi ln 9 over 4 or 2 pi ln 3 over 2. That's the same thing because you can bring the 2 up as an exponent and then that's 9 over 4. That's where that comes from. So this is what the answer was supposed to be, and then this is what the answer I got is. And so that tells me that somehow I'm supposed to have a 3 somewhere and I'm just not seeing it. Oh wait, you know what? 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 No, I still don't know. Sorry. Oh yeah, I do know. No, I don't. This is not u, right? U is supposed to have a 1 there. There's supposed to be a plus 1. So right here, there's supposed to be a plus 1, and I didn't even write it. But that was what u was supposed to be. So this should have had a plus 1, so this should have a plus 1. So this should have had a plus 1. So that should have been 3 halves. And so that should have been 3 halves, and that should have been 3 halves. And that should have been 3 halves, 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 and now there's no mistake. All right, sorry about that. One little typo, and then you can never find the typo ever. All right, so that's that. Now, I think you have to do this twice, and I apologize, but hopefully it'll be the same one or very close. Yeah. Hopefully it'll be very close. Just double checking that there's nothing else in here that's weird. Oh no, you do have one more that's actually different, but it's easier by a lot. Okay, yeah, okay, so we're good. So that's it for that lecture. So we're like hour and 10 minutes. I'm going to continue with this rather than starting a new video. So this is going to be like where the homework 19 starts, which is the other kind of improper integral. Other type. All right. So just to remember where we are, so the other type was like this. This was the type where the integrand becomes infinite. And I gave you an example, and my example was something like this. 1 to 5 of 1 over x minus 5 dx. Okay? And you can see, right, that the problem is you plug in a 5 in there and it's infinity. Divide by 0. Okay? But that's not the only kind that's a problem. You also have to worry about where there's a divide by 0 anywhere in the region you're integrating over. So like, but this is still a problem. Like if I go, let's say 2 to 6 of 1 over x minus 4, that's a problem because there's a divide by 0 at x equals 4, right? You can see that. Divide by 0 at x equals 4, and 4 is in the interval 2 to 6. Now, right, because you're integrating from 2 to 6. So that's why that's important. Because if the 4 was not in the interval, it's actually not improper. So this is not improper. If I say integral from 6 to 8 of 1 over x minus 4, that's fine because the divide by 0 is not in between 6 and 8. So no issue. Because on 6 to 8, there isn't a divide by 0. All right, so it's a little bit, you have to make sure you pay attention to know, or at least think about whether or not the problem is actually in your interval. Otherwise, it doesn't matter. So that's what they are. Like the divide by 0 is in the middle of the interval, basically, or on the edge. So basically, there's two cases. If the problem x value is a limit of integration, you fix it basically the way you did the other type. So you basically do the same thing as before. So an example would be like this. There's one extra complication though that I'll talk about. So like if I say integral from, let's just do 1 to 5 again, 1 over x minus 5 dx, what you're going to want to do is rewrite it as a limit, not as x, a limit as, let's say, b goes to 5 of the integral from 1 to b of 1 over x minus 5 dx. So that looks the same as what we did for the other type of infinite integral. But the thing is that you have to add that we have not done yet is this. So like on a number line here, right, you had 1 and you had 5, and we needed to avoid 5, right? So 5 is what we need to avoid, right? So to avoid 5, we must approach 5 from the left. Why is that the case? Because the region that we're integrating starts here at 1, and you don't want it to go like this, because if you put it past 5, 5's in your interval, and you're not allowed to have a divide by 0. So you can't draw the interval the way I just did it. What you need is you have to have your interval on the left, and then when we take our limit, the limit does that. So the limit takes you up to 5. But we're approaching from the left, so that's actually this kind of limit. So you have to write it that way. Limit b approaches 5 from the left. And the reason that matters is because sometimes you get positive numbers and sometimes you get negative numbers depending on whether you're on the left or the right. And so you gotta think about it a little bit. All right, we may as well just finish this because it's an okay problem. So let's do that. So we've got the limit as b goes to 5 from the left of integral 1 to b, 1 over x minus 5 dx. You can do this with a U-substitution, but we've done a lot of these in previous sections now. So I'm just going to say ln absolute value x minus 5 from 1 to b. So you've got ln absolute value b minus 5 minus ln absolute value 1 minus 5. Like that. Now, what's going to happen here is I'm not going to write that because we're taking the limit. When you put your 5 in here, you're going to have ln 5 minus 5. And here you're going to have ln absolute value negative 4. Now, that's absolute value negative 4, so that's actually just ln 4, which is fine. But this is ln 0. But ln 0 is not defined. Because if you look at a graph of the natural log function, it does this. So at 0, it actually goes to the limit as x goes to 0 from the right of ln x equals negative infinity. So this is not defined, it's negative infinity. So the integral diverges because we don't get a number. Okay? So that was, that's what you do. So you take a limit and then you do it. So it's exactly the same as the normal type that we've already seen, really. Not much different. I'm opening homework 19 real quick here for you. Okay, so the other thing you need to know is what about when you have the hole in the middle, right? So what about when I'll say discontinuity is in the middle of the interval. Right? Like this. So like if I go 8 to 10, 1 over x minus 9 squared or something like that. Right? Like what if you have that? So the problem is at 9, right? Well, what you do is actually very similar to what I said to do for the negative infinity to infinity limits, right? What you do is you split it at the discontinuity, which is, x equals 9. So the problem's at 9, so instead of doing 8 to 10, you do 8 to 9, and then you do a separate integral from 9 to 10. And then the same rules apply. What you would have to do is do both of these separately. And add up the results. And keep in mind, if one diverges, you're done. They both, like, the whole thing is bad. The whole thing diverges. Okay, so you just split it that way. And so I'll write it out for this one. So if we were going to do this one, the problem's at 9, so we'd have a limit as b goes to 9 of integral 8 to b, 1 over x minus 9 squared. Actually, I'm going to rewrite that, by the way. In order to do the integral, I'd have to write it this way. So I'm gonna do it. Now, which way would we have to approach from? Well, again, you got to think about your number line. So 8's here, 9's here. So you need to think about, like, well, we should be going from 8 and we don't want to get to 9. So there's my integral, and then we're going to come this way. So that's from the left, which is the negative side. And then the other one is a limit as, I'll say a goes to 9. That's an a of the integral from a to 10. Again, x minus 9 squared, negative squared. And then if you think about which direction the limit should come from, well, this is 9 to 10, so you have 9 and 10. So you're trying to avoid the 9. You don't want to go past 9, so you need to be on the right and approach that way. That way you don't cross 9. So that's from the right-hand side. And then you'd need to do each of those limits. So, or we need to do each of the integrals. So if I do the first one, it would be limit b goes to 9 from the left of, you need the antiderivative there. You can do a u-sub, but it's going to be x minus 9 to the negative 1 times negative 1 from 8 to b. Limit b goes to 9 from the left. Plug in a b, you get negative b minus 9 to the negative 1 minus minus 8 minus 9 to the negative 1. So this is negative 1 over b minus 9 plus 1 over, so I already did the negative from the negative, then I have 8 minus 9, which is negative 1. So like that, I believe. And we need b to go to 9. So b goes to 9 from the left. So if it's on the left-hand side, it's less than 9. So less than 9 minus 9 is negative. So it's negative, negative. So overall, this is going to be plus infinity minus 1. So it's plus infinity. Now, we don't actually care, plus infinity, minus infinity. So don't worry too much about the left and the right-hand limit. But we got infinity because of the, like when you put in a 9, there's a divide by 0, right? Because it's 1 over 0 is infinity. Plus or minus infinity. So this is infinity. So the integral diverges. Okay? So we don't even do the other one. Like there's no point in doing the other one because I can just say now that the whole thing diverges. All right, and so that's what you do. You just you split the integral at the problem point if there's a problem point. I'm just going to double check a couple of these to see if there's anything interesting. Oh, comparison theorem. Make you guys do the comparison theorem? That's terrible. Okay, so we have to do it. So there's also there's actually a limit comparison theorem and a comparison theorem, and I don't know if they're going to make us do both. They call it the comparison theorem, so I think maybe they don't. Oh, actually, before we do that, we can do it here. So I know this, right? 1 to infinity of x to the p. I already told you when that converged. I said it converges if p is greater than 1. And I said it diverges if p is less than 1. Less than or equal diverges. Now what I didn't go over yet, so this is new, is if you do an integral from, let's say, 0 to 1 of 1 over x to the p, what about that one? Well, this one actually converges and diverges opposite. So this one converges if p is less than 1 and diverges if p is greater than or equal to 1. And you'll notice that p equals 1 is here on the diverges side, and p equals 1 is here on the diverges side. So when p is 1, no matter what, it diverges, basically. All right, so you're going to remember these two things. And then the theorem is going to be, well, I mean, there's direct comparison, goes like this. Comparison theorem. Okay, so if 0 less than f less than g, so this is just because they need to be positive. The functions need to be positive, that's all. And it's not that there's not a theorem if they're negative, it's just that it would be awkward to write, so they don't bother. So the functions must be positive. So 0 is less than f less than g. Now, if you think about that, like on a graph, what this is going to look like is, I'm going to want these to at least have a chance of converging. So they're both positive, so they're above 0. So let's say this is f. And then g is greater, right? Because I drew it on there. So that's like that. Again, I mean, I don't know exactly what it looks like, but these are just made up. I know it's bigger, like that. Okay, and so the idea is this. If the integral from 1 to infinity of the big function converges, then the integral of the little function converges. All right? And the reason that's the case is because if you think about it, like the integral is an area, right? And so like if I draw the area under the big curve and somehow that's finite, right? Like if the area under the red curve is a finite number, like let's say it's 10, then wouldn't the area under the blue curve down here, wouldn't that also have to be less than 10? Like if the area under the red curve is 10, then the area under the blue curve is less than 10. So it can't be infinity, right? The blue curve can't be infinity if the red curve is finite, because the blue curve is smaller. And so that's the idea, and it's just written down here. So if the big function converges, then the small function converges. small function. All right, and you can turn that around and say, if the small one, which was f, diverges, then the big one diverges too. Okay, and that's the same reasoning in the opposite direction, because if you have, imagine that the blue one is infinity. If the blue area is infinity, how could the red area be less than infinity? It couldn't, right? Because the red area is bigger. So if the red area is bigger than infinity, then it must be infinity itself. Science has not discovered a number bigger than infinity. Nothing's bigger than infinity except your mom. I'm sorry, I shouldn't have said that. Okay, let's do one of these. So here's how you would use this theorem. You use it when you have an integral and you don't want to do the integral, or you can't do the integral. Here's how you use it. Sine squared x plus 7 over x squared plus 10. Okay, so, and we're not going to find the integral. We're just going to say convergent or divergent. That's all we can say. We're not going to come up with a number. Convergent or divergent. All right. So what you want to do is you want to compare this. The goal is to compare it, this integral, to a what I called p integral. Right? So if I can compare it to one of these, then I'll know whether or not it converges or diverges. So we want to compare it to one of those. So like in the comparison theorem, right, which talks about big functions and little functions, I need to compare this to either a big function or a little function. Okay? So here's how you go. So you just take the integrand and just pull it out to look at. So we've got sine squared x plus 7 over x squared plus 10. Now, this is less than or equal to 1 plus 7 over x squared plus 10. Why is that true? I know that's true because I know that sine squared x has to be less than or equal to 1, right? So that's why if I replace the sine x with a 1, I made it bigger because sine x is sine x is smaller than 1. So that is 8 over x squared plus 10. But then, what if I just drop off the 10? Well, let me not put that there. How do these compare? How does x squared, what did we do from here to here? From here to here. I made the denominator smaller, right? Because I took away 10. So I made the denominator smaller. If you make the denominator smaller, the fraction actually gets bigger. So that's that way again. Okay? So, the way you do this is, I can say this now. The integral from 1 to infinity of mine, which was sine squared x plus 7 over x squared plus 10 dx, it's got to be less than this one, right? Because remember, I'm paying attention to these. It's bigger, like going to the right, they're getting bigger. So it's bigger than this one. Or sorry, this one's bigger, right? Bigger, smaller. And what can we say about the bigger one? Does the bigger one converge or diverge? So you look at your integrals that you know. What's the p? The p is 2, right? Actually, the p is 2. So if p is 2, then we're here, right? P greater than 1 because it's 2. So it converges. So this is bigger and converges. Bigger and converges. And then the comparison theorem says that if the big one converges, then the small one converges. So smaller and bigger and converges. So if the bigger one converges, then the smaller one does. Since big integral converges, small integral converges. And that's it. That's the comparison test. Okay. Now I am going to look at these and we're going to cross our fingers that they don't do the limit comparison test, because the limit comparison test sucks. No, it doesn't. It doesn't suck, but I don't want to do it right now because we are 1 hour 35 minutes into the video. And I did not realize we were going to get there. Okay. Blah, blah, blah. All right, let's do one more of these. So, example, it's another converges or diverges. And I've got integral 7 to infinity 7 plus e to the negative x over x minus 7. Okay, so what? Oh, hold on. Whoa, all right, well, shoot. There's like two things going on here. So 7's an issue, right? You're not allowed to divide by 7, but also it's going to infinity. So I'm actually going to split this up into two. I'm going to say like 7 to, I don't know, 8 of 7 plus e to the negative x over x minus 7 dx. And then I'm going to do another one from 8 to infinity of 7 plus e to the negative x over x minus 7 dx. So the reason I'm doing that is because this one has the second type of improper integral, and this one is the first type of improper, and I don't want to have to deal with both of those at the same time. Okay, so I'm actually going to look at that second one there. So let's look at the second one, 8 to infinity of 7 plus e to the negative x over x minus 7 dx. Okay, so we want to compare this to something. So 7 plus e to the negative x over x minus 7. Now, if I do this, come on, have I made it bigger or smaller? So this is always positive, right? I know that, so e to the negative x is actually greater than 0. So if I replace it with 0, right, then the inequality is actually this way. Okay, so that's actually smaller. Why did I erase that? Okay. So that's why I can use this symbol. So I replaced it. Now the next thing I want to do is say, okay, well, what about 7 over x? How, like, from here to here, what did I do to the denominator? I made denominator bigger or smaller? Well, I went from a -7 up to 0, right? I made the denominator bigger. I made the denominator bigger. So the fraction is smaller, right? If you make the denominator bigger, the fraction is smaller. So it goes this way again. So I've got the integral from 8 to infinity of 7 plus e to the negative x over x minus 7 dx is less than the integral from 8 to infinity of 7 over x dx. So this is the big one, and then this is the small one. And what can we say about the small one? Does the small one converge or diverge? Now, I know it's an 8 here instead of a, it's an 8 instead of a 1 here. That doesn't matter, okay? Because it's all out, like what happens as you head out towards infinity. So let's look at the p integrals. So, well, what was p? p is 1 here, right? That's p equals 1. So if p equals 1, what does this say? If p equals 1, we're in this case, right? So the integral diverges. So the small one diverges. So the small one diverges. So what's the comparison theorem say about that case? The comparison theorem says that if the big function converges, the small function converges, and if the small one diverges, then the big one diverges. So if the small one diverges, the big one diverges. And in this case, the small one diverges. So you're able to conclude that the big one diverges. Since the small one, the small integral diverges, the big one, which is actually the one we care about, diverges by comparison theorem. So what can we say about the whole thing? The original one diverges. We don't need to check the other one, right? Like we only did this one, but we don't need to do the other one because remember, if one of them diverges, the whole thing diverges. You don't need to keep going. Okay, so let's see here.